All right, hi, I'm Martina. I'm presenting on tissue engineering of vascular grafts, multi-layer electrospun scaffold constructs. I worked with Dr. Anil Mahapatra in the biomedical engineering department. So tissue engineering is a field that involves engineering and science, so it combines those two to maintain, create, and restore organ systems and organs. So tissue engineering of vascular grafts or blood vessels is a subfield. The contributions that tissue engineering of vascular grafts could have would be indirectly helping the organ shortage, directly helping people with cardiovascular diseases and the effects of hypertension. So people with cardiovascular diseases like peripheral artery disease or atherosclerosis have vessels that churn bad somehow. And so when those vessels get messed up, they need to be renewed or helped. And so vascular grafts or implants can help those systems and restore the function of those vessels. So we're going to go into basic anatomy of the vessel system. So we have arteries and veins, and you can see on the right, arteries and veins. They both have a triple layer anatomy construct. So on the inner layer, we have the tunica intima, and the middle layer is the tunica media, and the outer layer is the tunica externa. So both of these vessels, veins and arteries, have that three-layer construct, and they only differ by a little bit of anatomy. Veins have valves and arteries do not. So going into each layer, what those layers do, the tunica adventitia, which is the outer layer of the vessel, it's made of mostly collagen, fibroblasts, and extracellular matrix. So the extracellular matrix in any system is kind of like a skeleton for the organ or in this case, the vessel. This layer plays a role in cell trafficking and immune responses. So it's interacting with things that are outside of the vessel and telling it what can come in or what's safe to interact with the blood that's inside the vessel. The tunica media is the inner layer of the vessels, and it's mainly composed of smooth muscle cells and then periocytes. So this layer is like a cardioprotective layer, and it can also promote angiogenesis or the creation of new material, and then it can prevent chronic inflammation and then reduce scar tissue. And then the inside layer, the tunica intima, so like if you're thinking of a tube, the inner layer of the tube, it's in contact with the blood. So if water is flowing through a tube, this is where the blood is flowing through the vessel. And this is made of mainly endothelial cells. These cells are special because they pack tightly together, but they allow for interaction with the next layer of the vessel as well. So this is like the structural integrity layer, and this is what biomedical engineers have to really focus on in creating a scaffold that is like a blood vessel. So for like any other engineering, tissue engineering requires a scaffold or a frame. So if we look at this picture right here, this is showing a building, and it shows the frame, the scaffold. It's like a skeleton for the building, and it matches the anatomy that the building will have. So for tissue engineering, we also need scaffolds, but they're not made of metal or wood or other materials. It's made of special materials that are not negative to the body, so that's called biocompatible. So for the scaffolds, in this case for vessels, they have to match the natural vessel anatomy. And natural vessel anatomy is a three-layer system, so we want to try and match that. So they become a tubular structure, much like this. This is just a graphic showing the anatomies again. So we need this triple-layer system somehow so that we can make a tubular structure accurately, and then we need to be able to fill that in with substance that's actually in the vessel. So if you think of a building, you're filling it with insulation or concrete. For our scaffolds, we're filling it with cells or proteins. And finally, we need to integrate this. When the vessel construct is complete, we need to integrate it into the body. And so one of the best ways to create a construct like this or a scaffold for blood vessel engineering is electrospinning. Electrospinning is a fabrication method, and it can very easily mimic the extracellular matrix of a blood vessel. So the process involves a polymer solution, a DC power supply, extrusion through a controlled jet stream, so it's like kind of like a syringe, and then a collector. So we look at this graphic. Here's our syringe. This is filled with a polymer, so it's called the polymer reservoir, and that can be any kind of polymer that the scientist is using to make their scaffold. So this material changes based on the study. And then we have our high voltage power supply. The voltage power supply creates both an electric field and it charges the polymer solution so that the polymer solution is able to flow through the extrusion needle here. And so when it's extruding through that needle, it becomes a fiber, and that fiber will collect on a collector. So in this case, we have a rotating drum mandrel, which is usually used for blood vessel engineering because we need to make a tubular structure. So electrospinning is also pretty special because it's very customizable. We can customize through the voltage that's applied to the polymer, and then we can adjust the flow rate of the polymer. We can also change the size of the fiber that's coming out of the needle and through this extrusion needle that we saw on the other page. And we're going to look at these three pictures right here. These are examples of electrospinning. And it might look like these are kind of a mess of fibers or there's a bunch of strings, but in reality, for tissue engineering, especially, we need these pores and we need that space in the scaffold because we have to allow blood to flow through it or allow cells to flow through that and connect here. So this is a very close picture of a scaffold like this. And this is our tubular scaffold that we need to create. So electrospinning also allows for sequential multi-layering. And the sequential multi-layering can be done with different materials. So materials that are used for blood vessel creation are biodegradable polymers, synthetic non-degradable polymers, and biopolymers. So I did a literature review, an extended literature review, and I looked at different materials, different material combinations, and how these can combine and different methods to create electrospun scaffolds. And so biodegradable polymers, these are the ones that I looked at, but there's actually lots more of these materials. So biodegradable will degrade in the body with time. Synthetic non-degradable polymers will not degrade in the body, and they're not natural. Biopolymers are natural things that are found in your body or in nature. So these two are usually used together, biopolymers and biodegradable polymers. So we're going to look at 3 case studies. In my paper, I looked at several case studies, but these are ones that really portray the things that electrospinning can do. So this is one study here. The first study is showing a guide. So this group of scientists created a guide that could direct cell placement and direct cell interaction, and then after that construct was created with a scaffold, it could be rolled up. You see right here, it could be rolled into a tubular structure. So this tube would roll along the cell sheet, and then it would create a structure that encompasses the cells and the scaffold. So in order to direct the cells, one of the things they used was electrospinning. So these electrospun fibers are all aligned in the same way, and that can actually direct cell growth. The second study we'll look at is right here. This is just showing a triple layer system that these scientists created. So they used PCl, polycaprolactone, collagen, and PLLA, polylactic acid, to create a triple layer system. And the triple layer system, like we discussed, is just the same as the vessel system that we have in our bodies. So if we can create a triple layer system or a multi-layer system, then it's going to be very similar and we can transplant easily. So the materials, what's cool about this is the materials can be changed through the electrospinning process that we saw. And this group of scientists used PCl on the inner layer because PCl is a biodegradable material. Collagen is naturally found in the second layer, and then PLLA just can act as a structure, a skeleton like the electrocellular matrix we saw. So the next study we're going to look at is this one. This graphic is showing a electrospinning system with a mandrel, rotating mandrel, or just like a tubular rod. And this is kind of like a mold. So the electrospin fibers are falling onto that mold, and they're creating the tubular structure. In this case, it was unusual from the other studies I looked at because it's using two different syringes and two different sources. So this one is actually a cell suspension, and it's being put onto the mandrel as well as a polymer solution that's being put onto the mandrel. So that's becoming a simultaneous creation of a bilayer system, which with a multi-layer system, it's really beneficial to mimic our blood vessels. So future considerations of multi-layer scaffolds, we can add bioactive components to these scaffolds, and those are things like immunosuppressive agents so that the body doesn't react negatively to the implant, biomolecules or biofactors, and these things can improve blood flow interaction or long-term patency, so that means that we can keep the blood vessel open for a long period of time. And we can also do some research on degradation rates. So scaffolds, when they're being put into the body, if they're biodegradable, they need to match they need to complement the degradation and regeneration. So regeneration of the body to make new tissues and the breakdown of the materials that we put into the body. We can also incorporate drugs into the process. So we can promote drug delivery systems or use drugs like heparin, which is a blood thinner. So sometimes when these blood vessels are placed into the body, the contrast can promote clumping or catching of blood and catching of different cells, and that would block our vessel, so that wouldn't work. So if we can incorporate drugs, that might help the system. So all of these things can potentially contribute to that organ shortage or the cardiovascular diseases that many of our families have. So here are my references.